All right, everybody, this is the second video, and I'm going to start with question number 10, which is where I left off in the last video. For this one, we're asked to determine if each is concave up. That means your rates of change is increasing in value. Concave down means decreasing rate of change. Okay, so we're going to do kind of like what we did a little bit ago where we were checking how the changes change. So t, we increase by 4, and then by 4 again, and then by 4 again, and then by 4 again. So I can see I have equal length inputs. Okay, we want that to happen. So now I need to see how my outputs change. All right, so 0 to 8, I went up 8. 8 to 13, up 5, 13 to 15, plus 2, 15 to 16, plus 1. Well, as I move down the list here, my rate of change is decreasing in value. So that means this graph must be concave down. Okay, so what's happening is the function values are increasing, but the rate at which they're increasing is decreasing. So the rate of change is decreasing, okay? All right. Sorry, I had a cat that was chewing on something that he shouldn't have been, so I had to kind of pause him. And you'll learn more about this in the spring semester, but the cat that I was specifically talking to, his name is sine, as in sine and cosine, as in trigonometry. You'll learn all about that in the spring semester, I'm sure. All right. Let's go ahead to the next one here. My apologies on that. This one, we're increasing by 4, by 4, by 4, and by 4. Okay, so my inputs are equal length. We want that. Outputs, minus 10, minus 5, minus 2, minus 1. As I check those outputs, as we move down the chart, negative 10 to negative 5 to negative 2 to negative 1, the rates of change are increasing in value. Okay, because remember, when you're in negative world, the smaller the negative, the higher the value. Okay, so what this means is that we are concave up. All right, excellent. Okay, now we're going to go to the next one. Maybe, if this doesn't act silly. Okay, on the next one, it says find the values of the holes, zeros, and vertical asymptotes. Okay? All right, before I do this, let's define them. So holes, canceled factor, no longer in bottom. Okay. Vertical, well, let's do zeros next. Zeros, uncanceled factor in the top. I say uncanceled because if you canceled it at all, then it's no longer an x-intercept, okay? Uncanceled factors that are left in the top. Those are your zeros or your x-intercepts, okay? Vertical asymptotes, I call those VAs. Those are going to be factors left in the bottom. So factors in bottom when simplified. Well, you know what? It really doesn't matter. Well, yeah, because if it goes away, factors in the bottom uncanceled. Or how do I want to word this? Factors that remain in the bottom. There we go. Let's say it that way. Factors that remain in the bottom after canceling. All right, that's probably just the best way to say that. Okay, so now when I'm looking at this, first thing I'm going to do is cancel things that can be canceled. So on the first one, I notice that I have x minus 2 squared, and on the bottom I have x minus 2 cubed. So on top I have 2 of those x minus 2's, and on the bottom I have 3 of them, okay? One thing that has really helped my students is to just write out all these factors separately. I know this is a pain in the you-know-where, especially for this last one. But trust me, it might help if you struggle with what this is, okay? All right, so there's my numerator, and in my denominator, I have 3x minus 2's. And thankfully, I only have 2x minus 5's. Okay, so if you think about it this way, and then start canceling out one by one, I can see I have a pair of x minus 2's. Here's another one. And I've run out of x minus 2's. Now I go to x plus 3's. I see those are gone. And then for the x minus 5's, I see one pair, and I see another pair, and that's all I have. So on top, what remains is x minus 5 to the power of 4. And on the bottom, we have an x minus 2 that remains. Okay? All right, so wholes are canceled factors that are no longer in the bottom. So I canceled x plus 3, and I canceled x minus 5. Neither one of those are in the bottom anymore, so x equals negative 3 and x equals 5 are going to be my wholes. Okay? All right. Next thing I'm going to focus on is I am going to focus on the things that are not canceled. All right, I still have an x minus 2 in the denominator, so that means I have a vertical asymptote at x equals 2. All right. When I look at the top, I do have this x minus 5 to the 4th power, but it was canceled. There were x minus 5's that were canceled. So that means that x equals 5 is a whole. And what we have is we do not have any zeros. Because zeros only occur when there's an uncanceled factor. Uncanceled meaning it never got canceled, that is still on the top. Okay, so this one had no zeros. Okay. All right, in this next question, it says a regression model S is constructed for a data set. The residuals from the regression are plotted and labeled. No, they're not. We don't see those. Okay. If we were to envision this, so a residual plot has a vertical axis, which represents the residuals, okay? And the residuals range from 1, 2, 3 above, and then -1, -2, -3 below. Remember, the residual line is your prediction. All right, so what they're saying here is point A is located at -1.3. So point A is about right there somewhere. And point B is going to be located at 2.5. So B is going to be up here somewhere. And we want to know if what we have here, we want to know which one is an underestimate and which one is an overestimate. Okay, you have to remember that residual is equal to actual minus predicted. All right, so point A has a negative residual, which means that the actual value was less than predicted. Okay, so negative residual means that actual is less than predicted. Okay, and what that means is that our prediction for that point, so if we look here, prediction is where that prediction line would be. Point A means since we have the actual values less than predicted, that means that our model actually was an overestimate. So A is an overestimate. Okay? So if A is an overestimate, I can eliminate choice A and choice C because those say that A is an underestimate. Okay? When I look at B, I can see that for this one, we have a positive residual. And what that means is that actual is greater than predicted. So what that means here is that my model is an underestimate of what point B actually was. So B is an underestimate. Essentially, the way to think about this is your prediction line for the residual plot, is your prediction line above or below the point that you're referencing? All right, if the prediction is underneath the point that's being looked at, then that means that your model underestimated. Okay. So if I look at this, A is the model produces an underestimate at A. Hold on, I think I actually eliminated the wrong choices here. Sorry, I was misreading those. All right. Actually, model produces an overestimate at A, that's good. Underestimate at B, that's also good. Based on the absolute values of there's greater error with model B than with model A. All right, when we look at that, B is further away from the prediction. There is greater model error than with A. So A is the correct answer here. When we talk about the error in the model is how far is our point from the prediction line. All right, and we can easily see that point B is further away from the prediction line than point A was. All right. Feel free to ask about that question again if this reasoning was just weird, especially because I goofed on that. All right, for these next ones, we're going to look at the calculator. And honestly, I can tell you now, we don't necessarily need the calculator for number 13. Just looking at this, figure shows from 0 to 13. Endpoints are labeled as we can see. Two other extreme are labeled with points B and D. C is the only point of inflection. TA, TB, TC, and TD and TE represent x coordinates at those points. Describe the rate of change in each interval given by telling if the rate of change is positive or negative. So that's looking at slope. And increasing or decreasing, we're looking at concavity. Okay. So from A to B, I'm going to highlight that real quick. So from A to B, this graph has a negative slope. Okay, so So we have rate of change is negative because of the slope. And rate of change is increasing because of concave up. Okay. All right, now I'm going to highlight B to C. So we're going to highlight that section. And in that section, I can see the rate of change is positive because it has a positive slope. And rate of change is increasing. And again, that's because it's concave up. All right. Then I look from C to D. From C to D, I can see that the rate of change is positive. And again, that's because we have a positive slope. But we're concave down, so the rate of change is decreasing. Concave down. Okay, and then finally we have from D to E. From D to E, I can see that the rate of change is negative. And that's because negative slope. Rate of change is decreasing. That's because it's concave down. And there we go. All right, 2 more questions. We could do this, all right? Maybe. All right. Question 14 says, use the semi-log plots, which I know we haven't talked a whole lot about, but I'm just going to show you how you can do this really easily. Semi-log plots mean that exponential values look linear. That's the only thing you need to know about that right now. So semi-log plots are going to make exponential values look linear. So when you're looking at an exponential plot, a semi-log plot, you want to see a line if we're looking at exponential growth. If we're looking at growth, it's going to have a positive slope. And if it's decay, it'll have a negative slope. Okay? All right, so on example A, we have a semi-log plot, and we can see that this looks like if I could draw straight, looks like it is a negative slope line. So that means that it is exponential decay. Okay. On the next one, I can see a line with a positive slope. That means we're going to have exponential growth. And on D, this does not look like a line at all, so this is neither. Okay. Now you might be thinking, Mr. Bear, that looks like exponential. Well, it does, yes, but it is not a semi-log plot. Another thing that you need to know about semi-log plots is that the y-axis is scaled by factors of 10 or some base. All right, so I have 10 to the 0, 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4. You can see those are powers of 10, factors of 10. All right, same thing here. If I look at this next one, 10, 100, 1,000, those are all powers of 10, okay? But when we look at this one, this does not look like a line. And in a semi-log plot, the graph should look like a line if it's exponential. I know that seems weird. We'll talk more about this when we come back from Christmas break. Okay, my friends, we have one last question here, and then Miss Majors did the FRQ videos. All right, so here we have for time t, from t 0 to 1, the number of people inside a large shopping center, is changing at the rate modeled by this function, where p is measured in hundreds of people per year. Determine the values of the relative minimum and maximum from the interval from 0 to 1. Then describe the real-world context of these, okay? All right, so for this, I'm going to have to pull up Desmos, okay? So I'm going to do that real quick. Please tell me I have the Desmos app on here. If I don't, I'll just have to, it's fine. I'll just go to the website. So as you know, you should be typing in College Board Desmos. Okay? And we go to the graphing calculator. And I'm going to put in here y equals. Now I'm going to tell you now, they use t's in here, but I'm going to use x's when I put it into Desmos. So negative 5x cubed. Arrow right. Then I have plus 5x squared, so plus 5x squared. Then I have minus x plus 7, so minus x plus 7. Here's my graph, and we're told to only look at it from 0 to 1. So I'm just going to focus on, here we go. So there's 0, here's where it's about 1. You know what, let me just do it this way, okay? X equals 0, x equals 1. Not 4, but 1. Okay, so now I'm going to look at this graph between the blue line and the green line, okay? Relative minimum is going to be here at 0.122515, comma 6.94334, okay? Relative minimum, so we have a relative minimum at, I'm going to write those ordered pairs. I lost them. 0.1225, comma, and that was 6.943. All right, now for the maximum, we're going to use that point, 0.544, comma, 7.130. That 0 could have been rounded up to a 1. That is true. All right, so now we have this, and we want to determine what these mean in the real world context, okay? So this means that at time 0.1225 hours, we had a minimum value of 6.943 hundred. I think it was hundreds, right? Yep, hundreds. Customers. And this one here means at time 0.544 hours, so a little over half an hour, we had a max value of 7.130 hundred customers. All right, that does it for me, and that does it for this part of the study.